Welcome back to NE 630, nuclear reactor theory again. So we will continue our business of solving the reactor kinetics equation. So last time we were looking for the solution for the one group, one delayed neutron group equation. And we showed that n of t is just n naught and c of t is just n naught again. Here you will have rho over rho minus beta e to the power of minus or plus rho minus beta divided by gamma multiplied by t minus beta divided by rho minus beta e to the power of minus lambda rho divided by rho minus beta t, and c of t will be just n naught rho beta divided by rho minus beta all square e to the power of rho minus beta over gamma t plus beta over gamma lambda e to the power of minus lambda r over rho minus beta t. So last time we showed or studied the case where lambda is less than 0, and I showed to you guys that you will have n of t. You start with n equal to 1, then n naught, n equal to n naught here. Then you will have this prompt drop. Then you will have the decay here. And I showed to you that c of t, again, is started at c naught, and c naught is nearly 1600 times n naught. And I showed to you that it decays with the slower decay, and this decay and this decay are similar, but here you drop from n naught to n naught to n naught multiplied by 1 minus rho divided by beta, I think, or no, something like 1 minus rho over beta. Okay, so let me concentrate here a little bit before moving forward. So this drop here, we noticed from last time, to give you the actual figures. Last time we have n of t equal to n naught multiplied by 0.87 e to the power of minus 958 t plus 0.13 e to the power of minus 0.68 t. So this will decay out very fast. Yes? So if you look at the first root here, which is rho minus beta divided by what? By gamma. What's the period, reactor period? So this is e to the power of t over t, tau. You can write this as e to the power of t over tau. So tau should be what? Gamma over rho minus beta. Yes? So what does it mean? It means that your neutron population drops from an initial value of n naught to this final value of n naught over 1 minus rho over beta in just 1 tau. Yes? And what's 1 tau? 158. Tau here is a measure of what? Gamma. What's gamma? The prompt neutron lifetime in the reactor. Yes? So in 1 prompt neutron lifetime, you lost pretty much all the prompt neutron contribution. Yes? And then you will decay with the other period. What's the other period? So the other period is rho minus beta divided by what? By lambda. So your period now tau, yes, with period now tau has lambda on it. What's lambda? Delayed neutron precursor decay constant. So your period will be proportional to the decay time of the delayed neutron precursors. And this is here. So what happened is your neutron population, when you drop your control rod in a scram, your neutron population dropped sharply, abruptly, because of the response of the prompt neutrons. In one prompt neutron lifetime, the prompt neutron disappear from the core because they were eaten by the shark or the big whale, in this case the absorber, neutron absorber, which is the control rods. Then you have to wait for the delayed neutron precursors to give birth to delayed neutrons, and those delayed neutrons will have some decay time that you cannot shut your reactor without waiting for those prompt neutrons to decay and reach to certain, let's say 0 power or whatever. Of course, you will see it here. Okay, guys? So you will drop from N naught to N naught over 1 minus rho over beta. So you kill this beast here. Then you will end up with what? Beta over rho minus beta multiplied by N naught. So if you take beta from upstairs and downstairs and you have the minus sign, this will give you what? Which is this was N naught over 1 minus rho over beta. Okay, so you drop from the N naught to the N naught over 1 minus rho over beta in just neutron generation time, and this is the response of the prompt neutrons. Okay, then you will decay with the delayed neutron decay time. Okay, guys, did you understand this? I want this to be clear in your mind that what's going on inside the nuclear reactor. So let's look for, instead of rho is 0.05 and it is negative, let's look for the case where you will have subcritical, subprompt critical. So it's a rho is greater than 0, but you are not critical in prompt neutron. You are critical in both delayed and prompt neutron. So we will call this subprompt critical. What does mean subprompt critical? It's delayed critical. That you are critical on both the prompt and delayed neutrons, but on prompt neutron alone you are not critical. So this means that K multiplied by 1 minus beta, this is the prompt what? The prompt component of the multiplication factor, and it is less than what? Less than 1. You are not critical on prompt neutrons, although you are critical in both prompt and what? Prompt and delayed. So here rho is greater than 0, but you still less than what? Less than beta. And let's assume that you insert rho of 0.0015, which is less than beta. For uranium 235, beta is nearly 0.0065. Sometimes they wrote it 75 or 65, but okay. So if you substitute here in this equation, this was what? Rho divided by beta minus rho. If you substitute in those two equations, you will get the following. N of t equal to N naught multiplied by minus 0.25 e to the power of 100 e to the power of 100 minus 100t plus 1.25 e to the power of 0.08 t. So this is n of t, and c of t will be just n naught 0.3125 e to the power of minus 100 t plus 1562.5 e to the power of 0.0 t. So what happened at t equals 0? T equals 0, n of t equals 0 is just n naught, and this will be n naught multiplied by e to the power of 0 is 1, so you have negative 25 plus e to the power of 0 is 1, 1.25. So 1.25 minus 25 is what? Is 1, so you will have n naught equal to n naught. And c of t equal to 0 is just c naught, and if you calculate this, you will get 1562.8125 n naught. Okay, what's if t now is greater than 0? Just at t equal to 0, you got n naught and c naught. At t greater than 0, what will happen? So the generation time is just what? What's the generation time? 5 10 to the power of minus what? 6. Okay, but this is not, this is gamma. But the generation time will be something like, let's say, few milliseconds or so. Yeah.
Should the exponentials be both the same, 0.02 or 0.08? Or any?
So I wrote it what?
Should that be 0.02?
2.
And those negative exponents?
What do you say? Those are positive exponent and those are negative exponent. So if you remember last time, we have one positive. If you are positive, we have one positive and one negative. If you are negative reactivity, you have both negative zeros of the equation, or negative roots. So in just a few milliseconds, which is just, let's say, generation time less than milliseconds. So the generation time, we knew that it's 10 to the power of minus 4 for thermal reactors, a fraction of a millisecond. What will happen? This piece here is what will be gone. So what happened for your equation here? For the n naught, you will have increase a jump in what? In n naught. Why? Because at the very early beginning you were what? 1. So 1, and now because you are at 0 and 0 time, meaning 1 and 1, so you were 1.25 minus 0.25 is 1. Now in no time you go from 1 to 1.25. Yes, guys? So you expect what? You expect you were here at n naught, and then you expect to do what? Oh, so you will go from 1 to nearly 1 point what? 21 on a very fast jump. So you will go from n naught to n naught divided by what? 1 minus rho over beta. Yes? Rho is what? 0.00115 and beta is 0.0076. So this is what? A fraction less than 1. And then you subtract a fraction from 1, it gives you what? A fraction. A fraction 1 over a fraction is greater than 1, so n naught would be bumped up. And this will give you the 1.25. So you go from 1 to 1.25 in no time. And this is called prompt jump. It's called what? Prompt jump. Why? Because it is the response. You take off the control rods. Which one is more responsive to you? The prompt neutrons or the delayed neutrons? Prompt. So what happens is, take off the control rods, you increase what? You decrease the sigma absorption, you increase the fission, so you will have a plethora, what do you call it? Plethora of neutrons coming out from the reactor in your face. Yes? Then what will happen is, once you got those, you are not critical on those. So you will not increase the multiplication of the core based on those only. So in order to, some of them will leak, some of them will be absorbed. So you have to do what? You have to wait for the delayed neutrons, and you will have something like this. Okay, guys? This is n naught over n of t over n naught, and c of t over n naught. C of t, although C of t, C naught is 1600 times, but I will just plot both in the same plot. But you have actually to look at another axis here for what? For C of t, and this point should correspond to what? 1600. Okay, guys? So you will notice that C of t will just increase what? Increase exponentially. Yes? So, do you think you will lose much if you click this one at 0? You lose nothing. Out of 1500, you lose nothing. So you do not see anything. So you are here, you do not have anything, but you will grow up with the same what? So you will have two barrel, more or less barrel curve like this. Okay, guys? So this is the prompt jump. So this is the second case. So we studied a subcritical case where rho is less than 0, and it is very large amount of reactivity, and we showed that you cannot shut down your reactor instantaneously. You have a prompt drop, then you have to wait until the delayed neutrons will come to you, and no matter what you will do, your periods, the power will decrease by a period corresponding to the lambda, the decayed neutron. So you have to wait 3-4 lambdas until your power will reach to 0 or something like this. Okay, guys? The second case is where your rho is greater than 0, but it is still less than what? Beta. And we showed that you have a prompt jump, and then you will increase exponentially, but with a slower period, and this period is corresponding to the delayed neutron lambda. Okay? So what's the remaining situation? So when you are sober critical on prompt, so it is sober prompt critical. You are critical on prompt neutrons only. What do you expect? Okay, so let's look. So we will substitute here on those two equations with the case of rho greater than beta, and we will see. So this is super prompt critical, and this is, or there's no need for this one. In this case, let's assume that rho is equal to 0.0115, which is greater than what? Beta. If you divide rho by beta, and beta is 0.0075 for uranium-235, you will obtain 1.53, the value here. So this is rho greater than beta by 1.53, and this is 1 minus beta multiplied by the multiplication factor is greater than 1. So you are super critical on those. The two equations, it will be n of t equal to n naught multiplied by 2.9 e to the power of 66.7 t minus 1.9 e to the power of minus 0.23 t, and the c of t will be n naught multiplied by 5.4 e to the power of 66.7 t plus 1563 e to the power of minus 0.23 t. Again, if you calculate at t equal to 0, this will give you n naught. If you calculate at c equal to 0, this will give you c naught. And again, c naught is the same, 1563 or 15 whatever 68 or whatever. But now, if we look at t greater than 0, we will notice that t greater than 0, in just, if you substitute with 1 second, this will give you e to the power of 66.7, which is 10 to the power of 28. So you will be in Mars. All of us will be in Mars because of the propulsion. But just substitute 1 millisecond, which is 0.001. This will give you 1.04 something, or 1.0 something. If you substitute with 10 millisecond, which is 0.01, this will give you 1.67. If you substitute with 90 millisecond, which is 0.09, this will give you 400. If you will substitute with 100 millisecond, which is 0.1, this will give you 800. So in a tenth of a second, your power will increase by 800 times. Okay, guys? Of course, when you work in the reactor, you do not want to be the guy who will raise the power to 800 times in 1 millisecond, because you will take Nobel Prize for the worst engineer. So you do not want to be in this situation anyway, because I think before they will give you the Nobel Prize, they have to give it to you in the hereafter, not in this life, because you will not be here anymore. So this is what the situation here. So what about the C of T? Again, just this is very huge amount. You will not lose anything. Let's assume that you have a T equal to 1. This is 10 to the power of 28. This is, you are talking about end of universe, and the other side where the other guy is looking to you on the face of the earth. So here, so it's very small. So even if you are talking about something like a millisecond or tenth of a millisecond, this will increase by 800 times. So this would be around 4,000, and this is what? And this is 1,500. So you do not lose much. So you still also will be governed by this very large period. So what's the change here? There will not be any, for both of them, there will not be any prompt jump or anything like this. It will be something like this. Okay, guys? Usually, if you look at your period here, should be what? Tau, or sometimes they call it T, capital, will be 1 over what? 66.7, and this will give you 0.015 second. So how much? 15 milliseconds. Your period is 15 milliseconds. So in this case, if we are talking about 1 watt, so in a tenth of a second, tenth of a second, you will go from 1 watt to nearly 1 kilowatt, 800. So it will be 1 kilowatt. Yes? So can you imagine in a second, you will go to something like what? 10 to the power of 28. And this is huge power, extremely huge power. So if your core will not melt down, you have to find something that will suppress this crazy increase in power. Yes? So in order to do it, we don't have anything to do it. Of course, if we will find sharks that will eat every one of those neutrons, and it will stay in the crystal structure of the fuel, for example. This is the crystalline structure, and you have fuel here, fuel here, fuel here, so you have shark here, shark here, shark here, shark here. So you will shield all of them, but this will not happen. So the only thing is the feedback mechanisms. And sometimes the feedback mechanism for the prompt critical will play a very important role. And this is what we will see in the next chapter when we will discuss the reactor dynamics. What causes the multiplication factor to change inside the core. So this is the reactor kinetics, is how the power will change with time. Dynamics is what causes the multiplication factor to change. We will notice that the Doppler broadening will kick in, and again I told you the Doppler broadening is the cross section will do what? You have your resonance will be like this. Then with time, what will happen? Broaden like this, then it broaden like this, and your flux will do what? So the flux will increase. So the fluxes here will be completely depressed, but the flux will do what? Will increase once this will decrease. So in effect, that if you multiply sigma by phi, you will increase the absorption. So this increase in absorption will reduce the criticality for your reactor back and will work as a negative feedback coefficient. So you are trying to increase the power will increase, the temperature will increase, Doppler broadening will kick in, and then you will get a higher absorption will decrease the multiplication factor, and then you will have a negative feedback coefficient that will try to suppress the core. Not all reactors, of course, will have a negative feedback reactivity coefficient. So usually for thermal reactors, you will have negative feedback reactivity coefficient, especially for uranium-235, but there is other isotopes that they do not have a negative feedback coefficient. And again, the best thing is if you will work as a reactor designer, to design a reactor with positive reactivity coefficient, and to work in a reactor and make it greater than rho greater than beta, so you will have a disaster because nothing will stop it. Okay, so this is the situation. Now, if we try to solve the one group diffusion equation, what will happen is I'll show you the two equations, and the two equations were as follow. The two equations are as follow. dn of t by t, this is for the one delayed neutron group, rho of t minus beta divided by gamma n of t plus summation, or this is for general lambda I ci of t, and dc of t by dt is just equal to rho of t minus beta divided by gamma n of t no, it's actually beta I n of t over gamma minus lambda I ci of t. So what happened is, when you try to solve this one, what happened is, if you are trying to look for the behavior, kinetic behavior of your reactor, you have two time domains or time spans. One is the neutron generation time, and you have either prompt jump in generation time scale or prompt drop in generation time scale. And then you have a slower time performance based on the decay of the delayed neutron precursors. Yes? So you have two time domains. One is very, very short, the other one is very slow. Yes? And we said that if your reactor change in rho, the change in rho, if it is uniform, so you will have a shape of your flux that will change with time, and you can predict the solution by those 7 routes. So you will write the 7 routes and you will solve the equation. Usually we solve this equation what? Numerically. If you want to predict the time performance of your reactor just on the very short time scale, which is the neutron generation time scale, to look for the prompt jump or prompt drop or whatever, you have to solve this numerically. And to solve it numerically, you have two domains. Yes, the finite difference scheme that you will solve for this equation, you have to make your delta t for solving the equation as very small as compared to what? The shortest time in the problem. What's the shortest time? Generation time is what? 10 to the power of minus 5. But you are talking about a slow decay of the order of a minute. So this would be extremely difficult in solving this problems. Okay? So if you try to solve for the whole domain of the problem, you have to solve for many generation time, many delayed neutron decay times, so that you will see how the reactor will perform in, let's say, an hour, 2 hours. But you have also to resolve the time scale of the generation time, which is 10 to the power of minus 4 or so, 10 to the power of minus 5. So in this case, because of this difficulty, people usually will do some approximation. They will say, I will consider that our reactor will just go from 0 to the value of the prompt jump in no time. It will go from 0 to the prompt jump value, which is from 1 to 1.25, or from 1 to negative 0.25, or from 1 to 0.25 in no time. So I will consider as if the prompt jump or prompt drop happen instantaneously, so that I will clear this effect from my problem. Then I will take care of what? Slow performance of the reactor. Okay? And this is called prompt jump approximation. So prompt jump approximation. And usually they will do this prompt jump approximation by just taking the dn by dt here equal to 0, and this will give you rho minus beta divided by gamma n of t plus summation of lambda I ci of t. So what will happen if you have your reactor critical at some point of time and your reactivity was rho naught, and then at certain time t you move your control rods from initial position to final position, so that you change from rho naught to rho 1. So in this case we can say that 0 equal to rho naught minus beta divided by gamma n of t plus summation of lambda I ci of t, and the equation at rho 1, the new situation for your reactor, will be rho 1 minus beta over gamma multiplied by n of t plus sigma lambda I ci of t. So this is before change, and this is just right after change. This is why I said that those two quantities will not change by much. The delayed neutron precursor concentration, here I have an equilibrium delayed neutron precursor concentration, CI, okay? And then I was at rho naught. And what happened is I moved the control rods to a certain position and increased from rho naught to rho 1. The delayed neutron precursors, they will not change abruptly. They have inertia. So you have to take time to respond, to increase or decrease. Because this is just, they have an equilibrium position, yes? And the equilibrium position is just what? The production, which is coming from what? Fission minus what? Minus the decay. And this will not change abruptly. You have to give it time so that it will reach to the second equilibrium position. So we will consider that just right after the change, I did not change what? The delayed neutron precursor. So if you subtract those two equations, you can cancel this and cancel this, and you will have rho naught minus beta. And if you multiply everything by gamma, so gamma will cancel out, and you will have rho naught minus beta multiplied by, this one will be equal to what? N at t equals 0, for example. We will call it N naught. And this is N at t equal 1. We'll call it N1. So this is N1 equal to minus rho 1 minus beta multiplied by N1. So N1 over N naught will be just beta minus rho divided by naught divided by beta minus rho 1. If we subtract, actually there's a positive 8. If we subtract those two equations, so there will be a negative sign here, a negative sign here. So this is the right equation. Now you can take n of t from here. N of t will be what? Sigma lambda I ci of t divided by what? Rho minus beta divided by gamma, so gamma will be up here. Take it and substitute in the dc by dt. And this will give you dci of t by dt equal to beta I divided by gamma multiplied by gamma summation of lambda I ci divided by rho minus beta minus lambda I Ci.
Where's the minus sign?
Minus sign where? In this equation, I flip the minus sign by putting rho minus beta instead of. Maybe you can flip this sign. Let me see if I made a mistake or not. You can flip this sign. Beta minus rho. If we are talking about one delayed neutron group, not the 6 groups, so this will be beta, and this will be what? Beta, and the summation will be what? Lambda C, and this will be lambda C, and this will give you at the end minus lambda C of t divided by 1 minus beta over rho. And the minus sign that Muhammad was asking about is here. And this is just called the Brombaut jump approximation. Okay, guys? So I will stop here, and next time we'll talk about experimental determination of the neutron kinetic parameters and how to do experiment to calculate the kinetic parameters of the reactor. Then I think next time also we'll get into the business of the feedback mechanism and how they kick in the reactor. Do you have any question? No questions? Okay. Thank you so much.